situated. Excellent. It'll fall mid-presentation. Okay. So, grab that out. And remember how I said in the last lesson, don't forget about chapter 18? Yeah. Okay. Look, as a chapter by itself, it's not essential. I'm just really paranoid that they're going to ask a question on it. But it's like common sense sort of stuff. But I'm going to go through a little bit of chapter 18, won't take long. And when you're studying for it, just these are the sorts of questions they might ask. They might ask about safety, like using a well-ventilated area, if using your chemical causes dizziness. Like a lab coat's not going to help you with that. And do not ingest, remember, if it's toxic. Okay, so they might ask you things like that. And I was just talking to Austin, do we remember that the sulfuric acid content is not examinable, the actual content of it? It was just examinable through a sac. So don't waste time memorizing the contact process and everything like that. But I was speaking to the VCAR lady and she said that they might, like yield obviously and all of that is still examinable, but that's part of really a later chapter, chapter 16. But they might ask you questions such as, why is this process not favourable? And you might talk about, oh, it's too expensive to do that or something like that, okay? So I'm going to talk about just the essential parts. Okay, so if you've looked at chapter 18, a lot of it's really, really long. A lot of it's irrelevant. They have these two types of ways. First of all, you guys just need to know about an industrial chemist and his purpose, okay? So, in industrial chemistry, yeah, we spoke about making sulfuric acid, right? But there are many other things that we could make in industrial chemistry. What are sort of the main things that the industrial chemist looks at when deciding on a reaction? Like, when looking at a reaction, when they pick a reaction, what are the important things?
Cost.
Cost is really up there, okay? That's all right.
The availability of reactants.
The availability of reactants, very good.
Where the place to be located.
Where the place would be located, very good.
Not to compromise
Location
health
of
and
a
safety
plant.
of
Health
citizens.
Excellent. So, and also minimising pollution and things like that. So a little bit of green chemistry. But basically, there are two types of ways that we can produce our products. These are spoken about in chapter 18. You don't have to know them, memorise them or anything. But basically, I wanted to tie this into fuel cells. Do you remember the purpose of fuel cells? Continuous supply of electrical production. And why are they better than, say, generating electricity through methane burning?
We don't have any pollutants that result from it.
So that's number one. So you're starting to think like chapter 18, which is good. Pollutants, no carbon dioxide emissions. Coal burning, we get sulfur dioxide emissions, which can lead to acid rain. But what else? Fuel cells versus methane.
We'll always have the reactants for fuel cells.
Okay, well methane's actually quite readily available. I was more thinking, what about the energy efficiency of both of them? How do they compare? Like methane, we burn methane, what do we get? Heat energy. What do we use the heat energy for? Excellent. So then we heat water, steam, powers turbines, so mechanical energy to electrical energy.
So there's less energy conversions in fuel cells?
Less energy conversions in fuel cells, direct chemical to electrical energy like every other galvanic cell. So therefore, it has a higher percentage energy efficiency. So we said that fuel cells, do you remember the sort of roundabout energy efficiency of them?
60-70.
60-70? Did you say 67 or 67?
I said 60-70.
Okay, yeah. So it is around there. And then methane, good guess. Methane, like a coal-fired power station or just, you know, a methane power
2030.
station? It's around 35, okay? So really close. Here, they might talk about like one particular industry wants to provide a continuous supply of reactants, where the other industry wants to just do one-off, giving limited number of reactants. And then, like, the interesting thing is, when would you use the second option? When would you provide a continuous supply of reactants? Like, just use common sense. When would we want to keep supplying reactants and keep generating products?
Like powering like electricity to like a town or something.
Excellent. When we need our product, like not just in the short term, but we need our product in the long term. There is a big demand for our product, okay? This is what chapter 18 talks about, but it's more common sense. Like, this one's for one-off things. If you just need something here and now, you would get a few reactants. But continuous flow processing, which you don't need to know the term, but it's if we want products all the time. So that's with fuel cells, we get this continuous flow of reactants to get a continuous amount of electricity. And so remember, to increase yield, reactants may be added or products may be removed, okay? That's also said in chapter 18, but what other chapter says that?
26.
Equilibrium 1, okay? So a lot of this is repeated in equilibrium. Alright, so in this case, this is from the VCAR one. Like, I don't know if you guys have seen it, but it just says, basically we're doing this process, okay? And they speak about it on the previous page. We're doing this particular process. Is it endothermic or exothermic? Endo. Favoured by what type of temperatures, high or low?
Hi.
So yield is favoured by high temperatures. How about if it was an exothermic reaction? Yeah? You get a conflict between temperature and yield. Why do you get this conflict? Temperature, yeah.
High temperature increases reaction rate, but it is not good for the yield.
Excellent. So we always want to increase reaction rate in the chemical industry because we want things now. We don't want to wait forever, yeah? Even though it might be, like we spoke about this in sulfuric acid, you get this conflict where you've got an exothermic reaction favoured by low temperatures, but if you use low temperatures, it's a slow rate of reaction, so you don't actually get that much per time, yeah? But you get a lot over time, which you're not really interested in, you want it now, okay? So they might ask you something like this, but in this case, we're doing this reaction, and it basically says that hydrogen, this is another way of doing this particular reaction, where hydrogen is removed, like that's what the diagram is showing. And it's saying, explain why the separation of hydrogen in this way increases the yield of hydrogen obtained according to that reaction. So what do we say?
So hydrogen is removed, which is a product, and that shifts to the right.
Excellent. So that's said in chapter 18 as well, but we did that in equilibrium. So you remove products, you basically driving your reaction to the right. Hey guys? Is that my whiteboard, that tiny? So small. Okay, doesn't matter. Alright, so costs, VCAR just, I don't know, whenever you get stuck, just think about costs. Again, with that example, okay, so costs, what things cost a lot of money that we've spoken about?
Platinum.
Platinum. What's that usually used as?
Inert electrode.
Oh yeah, very good. So you might use graphite instead of platinum. They both do the same thing. What else? We've spoken about costs in relation to gas chromatography as well. Helium costs a lot. So what do we use? Yep, so 78% of the atmosphere is nitrogen. It's really cheap and readily obtainable. What else?
Thin layer chromatography, the other one.
Okay, the
powdery
paper one.
stuff, yeah.
Or do you mean the pressure HPLC?
No, the powdery version.
So the thin layer versus paper chromatography?
Yeah.
Did they look at different samples?
No.
But yeah, so that sort of thing. Catalysts also cost a lot.
How about like making lots of pressure in the system? That would be big.
Excellent.
And temperature.
And temperature. Yeah, so they might say, like remember when we did sulfuric acid, if a reaction is favourable by high pressures, what does that actually mean? Its yield is favourable by high temperatures. I mean high pressures, sorry. High pressures, high yield. Where are there less number of particles, on the right or the left? On the right, very good. But rate of reaction, is that also favoured by high pressures?
Yeah.
Why might you use a low pressure? In the industry, they might actually use a low pressure and not like, you know, a billion kPa because it's really expensive. Yeah, it's cheaper, okay? So again, that's what this chapter talks about. So cost, catalysts, less expensive catalysts may be preferable, even though you might get a slower rate of reaction. Because remember, catalyst changes rate of reaction. Does catalyst change yield? No, what does it increase the rate of? Lowers the activation energy of both the forward and reverse reaction. Yeah. Okay, so pressure, high pressures, exactly what you guys said, and temperature, Claudia. So increases the cost. Choice of reactant to use in excess. There's like an example with O2 plus, can't remember what. Let's just say that we wanted to make sulfur trioxide, which we wouldn't actually want to make. Instead of using sulfur dioxide or something which is expensive by flooding, you know, increasing the number of reactants to drive the reaction forward, we might use oxygen. Yeah, oxygen, not pure oxygen because that actually would be expensive, but if we could just get air and use that as a reactant. So just try and think about things like that. And safety and waste minimisation. So the chapter even says the safest option is not always the cheapest. Okay, so like if we're getting hydrogen, yeah, like in the other example, we were collecting hydrogen. Why might that not be safe for a worker?
Is it explosive if you catch it on fire?
Yeah, so it's really combustible, releases a lot of energy, yeah, and it can be dangerous in an explosion sort of situation. But it might be much cheaper to collect hydrogen because it drives the reaction so much more forward, even though it compromises safety. So is it fair to say that cost is a little bit more important than safety? I don't know. Maybe according to Vika, not sure in the actual industry, it seems kind of dodgy. But, okay, so this example, so this is the same one with a different question. Identify one disadvantage of this method of steam methane reforming. So the method just in the picture. What are things you could talk about?
You got, it looks like you're adding heat,
You're adding heat.
and then the reaction is endothermic, so it will decrease yield. There's a little arrow there with heat.
But it's endothermic, so it increases yield.
Yeah, that's what it says.
But why is it a disadvantage?
That stuff like this.
That's okay. You tried to get out of it, but yeah.
What do you think?
Methane, we do want it to burn, so that's a good thing.
Hydrogen produced, which is very possible.
Yep, so we have safety. H2 produced, highly combustible. What else?
Is the catalyst, because it's got, I don't know if it's got gaps in between, would it be a benefit to have it more compact? Or
Yeah. Oh, what do you mean? So
I'm thinking of,
you could have it more compact.
I was just thinking of like chromatography.
Ah, so but a catalyst. What did we just talk about? Catalyst can be expensive. You can say that. So cost of a catalyst. What else could be expensive in that situation?
And temperature, keeping the temperature high.
Yeah, so high temperatures.
Are they adding steam there? Oh, is it just the H2O? Because that'll increase pressure.
Yep, so they're adding steam. That's actually one of the reactants,
Yeah.
H2O gas.
But you're adding pressure then, so it's going to decrease the yield because of the
Because of the small particles.
particles. Yeah. It's a little
But
bit
you
too-
do need
Yeah,
to,
it's
that's
like-
our reactant. Alright, anything else? What else might be expensive there?
Continuously taking out H2.
Continuously taking out H2? Are you saying that it's an expensive process? I'm not sure. We can't really tell how they're taking it out in that example. Maybe they're just removing, I don't know, maybe it's by diffusion because H2 is smaller than CO. But I'm not, yeah.
Is palladium expensive?
Yes.
I was just about to say that.
You're going to say that? When you're stuck, talk about cost, okay? And VCAR, this is very rare that VCAR will ask a question like this, but just in case. So PD, expensive, and catalysts. So anything that kind of seems extravagant, pick on that. Okay. So energy costs, okay? There are also, as you said, increasing temperature can increase the cost, but there are things that we can do. For example, this is also from the VCAR exam. We've got two reactions here, step 1 and step 2. You might notice one's endothermic, one's exothermic. And then the question asks, identify one way in which the energy efficiency of this method can be maximised. So using energy efficiency means you're inputting the least amount of energy as possible. Okay? Is there anything we can do?
We can use the heat that we produce in step 2 to force the first reaction because it's endothermic.
Yes, exactly. And actually I've seen this on 2 VCAR exams. It's quite common that they ask this question. If you've got a 2-step process, so in the chemical industry we require 2 steps to make our ultimate product. If you've got an endothermic reaction followed by an exothermic reaction, you can increase the yield of the endothermic by using the waste heat from the exothermic. So that would be probably the best answer, and I think the only answer that they'd accept for that. So if you want to write that in. Do we know where the question is? So use the heat produced in step 2 to increase the yield of step 1. Okay, working safely. As I said, only maybe one multiple choice every 3 or 4 exams on working safely. They don't really care about you guys enough. So we have spoken about a couple of things in relation to sulfuric acid. We said, you know, imagine if you spill an acid, what would be the best way to mop it up?
You put sand on it and then you have to like dilute it
Or
eventually.
neutralise it with the base.
Yeah, and neutralise it with a base eventually. Yeah. So if you say something like that, that's fine. They usually take 5 or 6 answers. One of them is just chuck some sodium hydroxide on it or, you know, a base to neutralise it. If you said all of those steps, like put sand first and everything like that, you just get a better answer than the rest of the state. But things like that. And, you know, the warning labels, they'll always tell you, like it'll say, highly flammable or something like that. How can we minimise that risk?
Don't light it on fire.
Don't light it on fire. So keep away from high temperatures or something like that. It always says store in a cool place if you've seen, you know, something flammable like hairspray or something like that. Okay, so you don't need to know the details of it, but basically there's this company, and it's covered by the Occupational Health and Safety. Hey girls. So in this case, I think we already said that under safety. You could argue that hydrogen being collected it's unsafe for the person to collect hydrogen as it is highly combustible. So you can think about pretty much the two things is cost and safety. Okay, and these ones you don't need to know obviously all of those categories. But Jess, do you remember what sulfuric acid was identified as? Corrosive, yep. Oxidizing, very good. And one more.
Toxic?
Toxic, yeah. But you don't need to know about sulfuric acid, but like you need to know that pure oxygen gas or pure hydrogen gas is explosive, is flammable. It's a flammable gas, okay? So just using your knowledge, applying your knowledge. Oh yeah, we spoke about that one. Inhalation of fumes may cause dizziness. To minimise the risk, what do? Use gloves. Wear a lab coat. C, right? So it's C. So it's D. Okay. It's D. And like part of the chapter questions for you guys was writing the NSDS thing. You don't have to do that, but just know that I always do it for all of your pracs, making sure that it's safe and that you guys sign your risk assessment like every other time. No, you probably could have done that more. But basically, it's just you have a hazardous substance, you put it through a machine, it tells you what hazards are associated with it. Like 0.1 molar HCl can be ingested. That's why I got the year 11s to ingest it. And they went home and told their parents. That was interesting. So, but it's not toxic. It'll tell you if it's toxic. And then I'll tell you guys, okay, it's toxic, so wear gloves so that when you eat, it's a less chance of you still having it on your hands and killing yourselves. Okay. So if it's a hazardous chemical. And then finally, waste management. Okay? That has been, we've spoken about that with alternative energy sources. Okay? We've spoken about how, and with biochemical fuels. We spoke about, you know, burning coal to generate electricity. What kind of gases do you get from that? CO2
Sulfur.
and sulfur dioxide. Yeah. So things like that. And then green chemistry. Do we just know what this word means? I was just scared that we might not know. Do we know what green chemistry means? Environmental stuff? Well, yeah, it's like a whole project to minimise waste, okay? It's not really about cost at all. It's about just minimising waste, preventing, you know, if we can prevent carbon dioxide emissions, then we will. Fuel cells don't release any carbon dioxide. It is extremely green in its approach. Okay? And then finally, the location of a plant. Where might you have your plant?
Away from the areas.
Yeah. So if you're, yeah.
Am I close to supplies of reference? Like near lakes or something, near water or
Exactly.
mines?
Yeah. So you want it near your reactants, availability of raw materials, proximity to markets, so wherever you're supplying it to. Cost and energy, like you're not going to open up a plant in Toorak because it would probably be too expensive to do that, but you will in like Altona Meadows because it'll be cheaper. No offence, if anyone uses Altona Meadows. Water supply, so exactly what you said, and cost of land, so things like that. So it's like, to me this chapter is really common sense. But
What about disposal of the waste?
Yes. So do you remember how we can dispose of waste, let's say, in a nuclear power plant? How do we dispose of
Underground.
So bury in landfill sites?
You put it in an air conditioned
Air-conditioned room, you remember that? In those buckets, keeping it cool. Anything else? Not really for that. Yeah, oh, do you remember in biochemical fuels, when we're actually making biochemical fuels, what we do with the CO2?
Do we give it to the companies?
Carbonated drinks. We can make carbonated drinks out of it. So just try and think of that when you're answering it. Smart, intelligent ways of using CO2. There's only a limited number of things they can ask you. So, that being said, going to do physics again. No. Oh, okay. So I'm going to skip that question because we pretty much answered it. But we'll do question 3. Do you remember how to do, or have we just done this and you want to just check your answers?
Is this from the net?
Yeah, this is the VCAR cell made from the net. Did you have it? Do you guys remember how to use that table to work out, remember the table, and it's like the amount reacted, the amount initially, the amount produced, the equilibrium table? Yeah? Did you want to just check your answers? I got 0.03 molar. Did we get that? Do you want me to go through it or?
Do you want me to take away stuff?
Yeah. Who wants me to go through it?
Me. I didn't do it.
Yeah? Okay. So, when phosgene, and this is good because it has a equilibrium table at the back. We'll do this whole question. When phosgene, guys who have done it, I know you've done it, Jen, you've probably done it. You've done it, Mandy? Oh. You guys can just do the neat one or something or just listen. Yeah. Okay, so when phosgene is introduced into a reactor, equilibrium is attained according to the reaction. Chlorine gas is green. Okay, so 0.3 moles of our reactant and 0.2 moles of CO are introduced into a 5-litre container. When equilibrium is reached, they tell us how much Cl is formed. Did we start off with any Cl2? No? Okay. So then the temperature was maintained at 40 degrees Celsius. What do you think the purpose of that is? To maintain the temperature at 40 degrees Celsius?
Keep it all gaseous?
They'll all be gas at room temperature. Chlorine. 0.03. What would be the purpose? What changes when we change temperature? K. K. So if we're trying to work out K, don't you think that we're going to have to keep the temperature constant because K will change?
Yes.
Okay, so I would just start off by drawing a table. What do they want me to find out? K. Okay. So COCl2 produces CO plus Cl2. It's all 1 to 1. So I just have the moles initially, the moles reacted, and the moles final. Better, equilibrium. Okay, so how much?
Is that supposed to be an L or an O? You wrote cocoa instead of COCl.
Oh, did I?
That's what it was.
What's the answer?
No, what's on the left-hand side?
Moles. Oh, moles initially. Oh, that's fixed it. Okay. Moles initially, moles reacted, moles at equilibrium.
I've got lollipops too.
Oh, right.
And then what do we need at the end to work out K? What do you actually need to plug in to work out K? Concentration at equilibrium. Okay, so how much COCl2 do we have initially? Yeah. CO? equilibrium, what information is given to us?
Point one, CO2.
Okay, 0.1 of this. Okay, so that automatically tells you that we've had the change is positive 0.1. Okay, because we started off with 0 and we ended up with 0.1. Yeah? So according to stoichiometry, 1 mole of this will break down into 1 mole of this and 1 mole of this. So you can use stoic to work out how much of this had to have reacted to produce 0.1 mole of Cl2. 0.1? Yes, because it's a 1-to-1 ratio. Guys, are you following? Okay, so we needed to have minus 0.1. Why is it minus? Because it's actually reacted to produce 0.1 mole. Okay, so it's not there anymore. So we only have 0.2 mole left. CO, how much of it, would that be a minus as well?
No.
Why won't it be? It's being produced. Now this is different to usually they give you just the reactants, yeah? But here they've given you the products. But still we know that we've had a reaction going this way because we've produced 0.1 mole of Cl2, yeah? Therefore, we would have also had to produce 0.1 mole of CO. We started off with 0.2. How many moles do we have at equilibrium of carbon monoxide? 0.3. And then, how can I change them into concentration? Divided by 5. 0.04. 0.02. Okay. And then I just substitute it into my K expression for K, which is concentration of products over reactants. Do you have to put states in these brackets? No. Oops, CO. So we should have, this was Cl 0.02 times 0.06 over 0.04. 0.03. Now, getting the units, remember that that's in molarity times molarity over 1 molar. So what units am I left with? Just m by itself, because it's m squared over m to the power of 1. So this should be our answer. Yep? Are we happy with that? Brandon, did you work out why you went wrong? Was it? Yeah.
Miss, what percentage they got that right?
This was the 08 practice exam.
Okay.
It wasn't actually set by the state when they changed the study design. So calculate the numerical value of the equilibrium constant for the reverse reaction. What do we do for that?
Negative reciprocal. Oh, just the reciprocal, isn't it?
The reciprocal of 1 over
0.03.
0.03 gives us
33.
Good job. 33 m. Does this change the unit? Yes, because now it's m over m times m, giving us m to the negative 1. Yep. It's just math. So, next one. Explain why constant pressure may be seen as an indication that the reaction is at equilibrium.
Oh, didn't you explain that before?
I think that was temperature. We were talking about temperature. So explain why constant pressure indicates that this reaction is at equilibrium, or any reaction. Remember that when we're at equilibrium, what doesn't change?
The rate of the reverse and forward reaction.
If I add a catalyst, is it still at equilibrium?
Yeah.
But you can increase
But
the
there's
rate
Oh, but like relative to each other.
relative to each other. So they have the same rate. Pressure doesn't change, concentration doesn't change. That's how you can tell. The concentration is constant of reactants and products, and the pressure is constant if it's a gas. So, but explaining why. How might we explain that for 1 mark? If it wasn't at equilibrium, let's say we had a shift to the right or a shift to the left. Let's say actually we had a shift to the right. What would happen to pressure? Increase. If we had a shift to the left? Alright, so let's explain why at equilibrium we have a constant pressure then. It's hard to explain it, as we talked about last time. Who has a good explanation, do they reckon? No one? Okay. So, we could say something like, at equilibrium, would you talk about the fact that the rate of the forward and reverse reaction are equal? At equilibrium? Yeah? So you can start off like that. That doesn't really explain it though. What else might we say? The concentration stays constant, yeah. But the pressure, so we're talking about a gas. To be honest, I would probably talk about it like by describing if it wasn't at equilibrium, you would get a change in pressure. I would say, if the reaction So I would probably just explain it with the second point. If the reaction weren't at equilibrium, as there are more particles on the right and less on the left, we would expect an increase in pressure if there was a shift to the right, or a decrease if there was a shift to the left. So the reason why they're asking this question with this example is because you actually have, a different number of particles on the right to the left. Because if we had the same number of particles on the right and the left, would we be able to tell if it was at equilibrium based on pressure? No. Okay? I think they really want you to talk about that there are more on the right than the left. But then again, it's only 1 mark, and they haven't given us... Oh, actually, they did give us solutions. Let's see what they said. My desktop is bad. Is it? So where is it? Did I put it on Edmodo? Probably do better that way. Where's that? Dropbox. Oh, I can't even see it. It's hidden.
Dropbox is in the middle, centre.
Here. Oh, it's usually up there. Okay.
Let's watch Inside North Korea, part 1.
That's my year 10 home group. Okay, question 3B. Let's see what they said. Okay. When the reaction is moving forward or backward, there would be a change in pressure pressure due to the change in moles of particles. If the pressure were constant, this indicates that the forward and reverse reactions are occurring at the same rate. Hence, the system is at equilibrium. So pretty much what we said, they described it like if it weren't at equilibrium. But look at how much that is for 1 mark. But I don't see how you could answer it shorter with perfectly answering the question. Okay, so, I just held up all the answers to the other questions. Okay, so equilibrium mixtures were subjected to changes. Complete the table by indicating if it is a deeper green, lighter green, or if it's unchanged compared to the initial equilibrium. So here, what's coloured?
We have chlorine gas.
So Cl2 gas is coloured. And COCl2. Okay, let's have a look. Would it be more green? I.e., what are you going to be looking for? Sorry? Yeah, so you're just going to look if you're getting more chlorine or less chlorine compared to initial. Really? Because that's the only thing that's changing the colour. So, increase in volume. What happens to pressure? Decrease in pressure. Which way does it shift? Right, very good. So we get, what, something that is
Greener.
more green. Deeper green. Increase in volume. Decreases pressure, moving to the side with more particles. Yeah. Okay, addition of more carbon monoxide.
Let's go next.
Is this lighter green? Because once you increase the volume, you decrease the concentration, and then it goes back to original.
To the concentration. Oh, yeah, you're right. Yeah. Okay, that is something that trips a lot of people up, including me just then. Okay, so remember when we get that change in equilibrium? Thanks, Jen, for telling me that, otherwise that would be bad. Okay, so we can plot concentration versus time. What happens to the concentration of all three when you increase the volume? Decrease in concentration? Yeah? Which one's affected more? I.e., are we going to get a net forward or net reverse reaction? Net forward reaction. So let's say if we've got Cl2 here, CO here, and CO, Cl2, what's going to happen to that line as it reaches new equilibrium?
Oh.
Yep. This one, increase.
But it's still not as much as it did.
Still not as much as it is originally. So, yeah. Really, as soon as you change, it's the same with acids as well. Let's say if you had a weak acid, if we diluted this weak acid, what would happen to its pH? Increasing pH? Yep. Why?
Once you decide more particles, switch, and you don't have H2O, so that's the right in this, which increases the concentration of H2O plus.
We should decrease pH though.
Yeah, right.
But we get an increase in pH.
Yes, that's right, because
Isn't
Think about it. You add water to anything, what are you going to do to the concentration of H2O plus? Yeah. There's no way we can add water to an acid and make it more acidic. Yeah? So you're going to decrease that. It's not going to decrease as much as you'd expect if it was a strong acid, because you get a net back reaction. It will never reach the concentration that it was initially. But remember, it was even like 50% in the example we did. So it's quite good, but it's only partially opposes the change. So in this case, you will get lighter green. Okay, so let's write that in, because it never reaches its initial concentration, original concentration. Addition of more carbon monoxide. Addition of more carbon monoxide gas. Lighter green. Okay, so you add products, therefore you shift it to the reactant side and you consume some of the green chlorine. How about adding a non-reacting gas? Doesn't change. Yep. All right, let's see. I have a feeling that they had deeper green. Did they? No, they had lighter green. Okay. Unchanged. All right. How about part II? Which of the above changes would lead to an increase in the value of the equilibrium constant? None. Yep, because what is the only thing that changes the equilibrium constant? Temperature, yep. Briefly describe how you could determine whether the forward reaction is exothermic or endothermic. What could we easily do because we have a coloured product? So this is green. If we increase temperature and it's exothermic, what will happen to the amount of chlorine produced? Decreased. So if it's exothermic, you'd have to describe, do you mean endothermic?
Yeah.
So if it's endo and we increase temperature, we expect to get more green. Or you could use their words, deeper green. But if it's exothermic and we increase temperature, we expect it to be lighter green. I really think that they would want you to explain it like this way because it directly relates to the table.